and also to have been honored by having the last slot, which some people may consider a tragedy or a punishment, but for me it's a great honor. Yeah. Okay, so I will tell you about some work we did on these multiferroics, just as a brief introduction to multiferroics. Well, maybe everybody knows about these materials, but when I started to become interested in them, I had to Google what was a multiferroic. So I will say a few words about that. And I will talk about a mechanism which has to do with the lattice that couples magnetic and electric degrees of freedom. And this is work I have done with my collaborators in University of La Plata, Rossini, Pili, Borsi, and Grigera, and from Rosario, with Dobria and Gaza. And okay, so there are some publications already on that, which I'm going to summarize today. And so this is more or less the plan. I will be brief on each of these items, but first of all, I will talk about what is multiferroicity and about the possibility of switching electric polarization with a magnetic field or a magnetization with an electric field. And so essentially, I will concentrate on the magneto-electric coupling for collinear magnetic structures, which are a particular type of multiferroics, and in particular concentrate in the role of phonons. And so I will discuss this toy model in 1D and 2D, which we call the pantograph model because of a very old toy that had this shape. And what I will show you is the results that we have obtained, that through the lattice, you can couple electric and magnetic degrees of freedom to get a macroscopic switch of the polarization with the magnetic field. And well, the mechanism is by a proliferation of solitons. And then I will say a few words about fractional excitations that have this mixed combination of magnetic, electric, and elastic excitations. And then I will say something for 2D systems, and then conclusions and perspectives. Okay, so what is a multiferroic? A multiferroic is a material that has some new things. So for example, you can vary the polarization, electric polarization with a magnetic field, or otherwise magnetization with an electric field. And this is what people are looking for now, mainly this part here, because the idea is to use these materials to be able to write magnetic information using electric fields, which are much cheaper to generate. There are famous materials like bismuth ferrite, which has this structure, which is multiferroic. And normally there are many materials, or everywhere in nature there is a multiferroic coupling. I mean a coupling between electric and magnetic degrees of freedom. The problem is that technically these couplings are usually very small. So what people are looking for now are materials where this is a more important effect. And well, in general, what happens is that there is some distortion of the Young-Teller type at low temperatures that generates some polarization. And then you want to see whether a magnetic field can modify this structure to get a modification of P. And this is the particular type of multiferroics I will discuss today, which are called type 2, because in this type 2 multiferroics, both transitions occur at the same point. That means ferromagnetic or antiferromagnetic and a ferroelectric transition. And this is improper. And type 2 means that, type 2 means that, and improper means that the magnetic structures are collinear. There is a different kind of multiferroics, the first ones that were analyzed, studied, and discovered, which have the origin of multiferroicity is based on spin orbit effects and Yaloshinsky-Moriya couplings. And in those cases, magnetic structures are spiral type, non-collinear in general, non-coplanar. This is another class of multiferroics where one of the important characteristics for what I'm going to say today is that magnetic structures are collinear, okay? And in particular, so I will signal these two important properties: magnetic collinearity of the up-up, down-down type. So what I mean with that is that if you look in one direction, you will see something like this, and so on. And so there are quasi-one-dimensional structures which shows this. But there are also, for example, this is one of the most famous materials that shows this structure in the magnetic ordering. But there are also two-dimensional and three-dimensional materials that show this. I think we heard something about nickelates, and these nickelates show this structure up, down in the three directions of the crystal structure. And so this is the first issue. And the second issue is that there are simultaneous transitions. So if you look at the magnetization as a function of the magnetic field, so this is something like this. So you have a jump at some critical magnetic field of the magnetization. This is nothing very strange. But at the same time, what happens in many of these materials is that the polarization goes to zero. The electric polarization goes to zero at the same value of the magnetic field. Yeah? OK, so this is a long list of materials I will not discuss, but there are some. Oh, sorry. I wanted just to point out that these are quasi-two-dimensional systems. Nickelates I have already mentioned, which are 3D. And most of these double perovskites have a quasi-1D structure. OK, so the experiments, for example, this is one of the double perovskites, which is quasi-1D. And in this paper, they have shown what I have just designed there. So you see you vary the magnetic field. Magnetization increases abruptly at the same time that electric polarization drops off, okay? So we are going to try to discuss a simple model that has these two features. So the double transition together with this magnetic ordering. Okay, so these are other materials, never mind. This is another one of these double perovskites that also shows vanishing of P at the same point where M increases. There are also other cases that are related in some way. For example, this nickel vanadate has some magnetic one-third plateau. If you look at magnetization as a function of the magnetic field, you see that there is a one-third plateau here. And when you look at the polarization or the variation of the electric polarization, when you go in and out of the plateau, you see that there are changes, while there are no changes within the plateau. So it's a kind of similar situation like here. So here you have a big change when you go out the plateau, but nothing changes within it. And here it is the same situation, but in a higher magnetized state. Okay, and there are other cases too. This is, okay, this is, okay. This feature here also is observed also in some non-collinear multiferroics. So for example, in this terbium manganite, you see a big drop-off of P at the same place where, well, I don't have it, magnetization curve here, I think. But here, the same thing happened with the magnetization, just to say that maybe there is something deeper behind. OK, so let me go to the model we proposed. So essentially, the idea was to simplify this structure into this. So what are these arrows and dots here? So essentially, we have a magnetic system, which are the black dots. So we started with a spin-and-a-half system, but could be higher spins. And due to the electric environment, so some different electric charges or whatever is around this within these units, so it could be, for example, the Yantel distortion that creates some polarization, electric polarization. So we mimic this with I will start with a 1D case where you have spins on a line, and then you have some electric polarization that could be there before the formation or simply could appear because of the deformation. But the main idea is that when this guy distorts, for example, if this gets shorter, this will get larger, and then the polarization will be bigger, okay? So this is what we call the pantograph effect. And this is how we simulate this. So PZ is the Z component of the electric polarization. So you can have a sign here that can point up or down. So this is an Ising variable. Delta is the deformation, and this is some constant, and this is some fixed value. So this is the case of already present electric polarization that gets larger or smaller depending on how this the octahedron deforms, okay? Also, we will include a dipolar interaction that is turned out to be very important. And for the magnetic system, and this was inspired in previous papers that were talking about, they call it, well, I forget the name now, but there's a magneto-striction scenario. So this is the so-called and well-known spin pious Hamiltonian. So you have, these are the spin variables interacting via exchange. So these are these black arrows here. And with the new ingredient, no, it's the ingredient that makes it a spin pious system is that the coupling between the neighboring spins can vary depending on the distance between them. This is kind of trivial modelization. And then you have the elastic energy here. So you see, here you have magnetic units. Here you have these electric units, let's say, but they are not coupled directly. So delta is coupled to S, and delta is also coupled to P. So there is that's why the title was elastic connection between electric and magnetic degrees of freedom, okay? So, okay, so this is simply repeating what I put before. So I put together this spin pious Hamiltonian plus this energy, and the coupling is in here with the dipoles with the deformations, okay? So, and then the rest of the talk will be the discussion of these models in different situations. So this, we started with, because of professional deformation, with a spin 1/2 case, because this was the example I knew better. But I have to admit that this, all these materials I have talked about before are typically Ising-like, okay? So there may be some XY components, but the main direction of the magnetic units is along some definite crystal direction, okay? This, we improved this a little bit later. But let me just discuss this simpler case. So if you look at the purely magneto-elastic model, that means what I call the spin pious Hamiltonian. So you have spins and phonons. Well, here these are just deformations, classical deformations, but it can be extended to more general phonon case. We have studied this long time ago with Poil Blanc and some of my actual collaborations when I was in France a long time ago. And we have seen that there were interesting features in the magnetization curve once you consider these elastic degrees of freedom. So for example, this is the simplest case. So here you have a magnetization as a function of the field. So you have a spin gap, so a magnetization plateau, like here. And this magnetization will grow up in some way after you overpass this spin gap. And this is what happens in the excited state. So I will draw a cartoon here. So in the zero magnetization situation, you have classically something like this, which is not true in this case, but for the ideas I want to discuss, the picture is similar. So of course you can have this guy or this guy, okay? So you have two possibilities for the ground state, either these or singlets on the shorter bonds. And if you create one excitation, let's say one magnon, this is what happens. So the system, this is DMLG results for periodic boundary conditions. So what happens is that when you create a magnon here, so you flip one spin, and then this spin will divide into two spinons, okay? Well, this is all well known, but I want to insist a little bit on that because it will be important for this, this characterization here. So essentially, well, I have also borrowed this material from an older paper where they have studied what happens. This is what happens when you create one magnon, so you have two spinons, and if you create many, essentially the excited states divides into two regions, which I call here P, 0, and 1, which are regions that have either this structure or this structure, okay? So why is it important? Okay, okay, we have done bosonization, but I will not discuss this. okay, why is this important? Is because, okay, so there are two deformations that, okay, this looks pretty fancy, but it just means this and that. So you have two ways of alternating deformations. So essentially, deformations that you have is that you get two guys close by and two far away, or the other way around, okay? So this is now the distorted lattice, okay? And depending on the couplings, it will arrange this way or this way. And now the question is, what happens if you increase the magnetic field? So this is a simplified version. So you have here spins, distortions, elastic energy. And this is the coupling that you have between the electric degrees of freedom and the lattice. So what happens if you increase the magnetic field in this system? So essentially, what you will get is you will create these two different regions. And let me go back to this pantograph thing. So essentially, here you have something that looks like this. And here you have something that looks like this, okay? And like this, okay? So here are the spins, and here, and this is one deformation. So here, for example, if originally the dipole was up, this will get longer, and this will get shorter. And this will get longer in an anti-ferroelectric scenario. So you see that if you change from this ground state to this ground state, the opposite will happen. So here you have a positive polarization pointing up for this case. And for this case, you will have the opposite polarization. And this is, in fact, behind this behavior here. So essentially, when you distort the system will be in one of the two degenerate ground states with one given polarization. So that's why you have this here. It's low magnetic fields, but once you start creating magnons that split into spinons, then you divide your system into regions like this, and then you will have half of this, and polarization will be zero. So this is the essential mechanism. And so this was what I was advancing, not yet this. So you have magnetization going up, and then at the same point, polarization going down, which is observed in many materials. So this is DMRG, so nothing new, but just to verify what we have obtained first by bosonization. So you see you have here polarization going sharply to zero, while magnetization has important growth at the beginning and then goes smoothly. And this is the ground state, and these are one of the ground states, and these are the excited states where you see that these guys are like I described. Okay, so there are other issues that I will not have time. How am I doing with the time? What? 12. Okay, thank you. Okay, so maybe I will say a few words. So one thing I discussed was this jump of P. So this is varying varying electric polarization. This is a new thing with a magnetic field. So the question is whether you could do the opposite. That means varying magnetization with an electric field. And this can be also done because the magnetization curve looks like this. So you have some plateau at 1/2 here. So if you put a magnetic field to go around here, then you can go from one magnetization to another with an electric field. So this is a bit longer to explain. I will be here today and tomorrow at the hotel. Otherwise, I am available online almost always. But essentially, you can also change with an electric field. You can change the pattern of the formations. This is the main message. So with the electric field, since they are coupled, so the dipoles are coupled to the formations. So with an electric field, you can change the deformations from dimerized pattern like this to something else, and then homogeneous. And then you could modify the magnetization with an electric field too. This is less interesting because, as I said, first you have to put a magnetic field to go up there, and then it's not so cheap anymore. So we are still working on that. So this is a summary of the results that I will not repeat. So you can change polarization with a magnetic field in a very similar way as in experiments. And and you can also vary this magnetization with an electric field. Okay, so this is, just look at this first line here. So now we wanted to go closer to experiments to reproduce this structure. And as everybody knows, this structure appears in, if you put second neighbors in some situations. So we added that J2, that is second neighbor interaction. And we also added that this non-isotropy along Z. Okay, so the two new parameters are a coupling J2 and the coupling delta that gives more weight to the SZ-SZ interaction. Okay, and in this region, which is corresponds to delta large, so mostly Ising spins and J2 over some value, this is kind of antiphase. So essentially here you recover this magnetic ordering, and all the rest that I discussed before, this remains unchanged, okay? Well, I will not have time to discuss this, but if you look at the excitations now, there are interesting combinations that happen at the same value of the magnetic field, but they are in different positions in the system, but they are combinations of magnetic, electric, and elastic fractional excitations that we call MM-ions or muons, whatever. Okay, so let's move to the 2D case. I will go a bit faster here. The idea is the same. So here, for example, I took as an example the phase diagram of the nickelates. And at the time I was giving my seminar on this 1D case, Marisa Medarde came to me and told me, look, in the nickelates we have also this up-up-down magnetic structure in the 3 directions. So I started to look at some 2D to begin with, to go upper in dimensionality. And I found this paper, well, this a review paper by Cheng and Mostovoy, where they were proposing that some deformation could lead to this polarization in some direction, just in this way, as a graphic way. And I connected it with some work that was done in an Ising model, magnetic Ising model coupled to lattice distortions that could give also this deformation. So we studied a model, a simplified model, that, is a 2D version of this. So that means that, okay, here I borrowed some pictures from other papers on the web. But essentially, if you look at the, I don't see one. So if you look, for example, at the white, how do you call this? It's not a square. Rhombus, no? This guy, this square, the form square. Okay, if you look at this line, so you see that here you get this structure, and also here, okay? So this is what we did. We proposed exactly the same situation in a 2D model. So the Hamiltonian now has Ising spins because 2D is more difficult, so we started with a simplified system. Also with this spin bias deformation type coupling. And on the sides here you have the polarization that will appear if there is some deformation. And essentially the ground state that we obtained is this up-up-down structure in both directions. And just to give you the final result, once you put dipolar interactions, you see clearly, so violet here is electric polarization, that you have a critical magnetic field that kills the polarization. At the same time, look at the orange curve, in which the magnetization grows, okay? And this is, again, this situation here, and also with this up-up-down structure, okay? Of course, there will be neutron signatures because of this spin channel ordering, and also because of the deformation. So this is the obvious outputs for the structure factors. And okay, so essentially the pattern is something like this. So short, long, in the 2 directions, okay, in some particular way. And importantly, as in the 1D case here, the dipolar interactions are very important, which are usually disregarded, but precisely it is the dipolar interactions that selects this particular ground state, so what we call the striped, because you can follow stripes of the same direction spins like here, and well, that's a particular name. Okay, so let me conclude. First, Well, I have shown you that a very easy model that connects magnetism and ferroelectricity via the lattice. In both cases, 1D and 2D, we could reproduce at least some qualitative facts. And so this magnetization jump at the same moment, at the same magnetic field where the polarization goes down in both cases. There was a funny second discussion with Marisa Medardo when I came back to her with a 2D realization, very happy, very proud of it, and she said, yeah, look, but this is 2D, our materials are 3D. So now we are working on the 3-dimensional version, which can also be done in this simplified picture, no? Because these are Ising spins and classical deformations. So it takes longer, but in principle there is no technicality that will avoid this. Okay, so and the second part is, okay, so for example, what you can do is you can have some electric polarization, let's say positive, and then grow the increase the magnetic field to kill this polarization. So you go there, and then with a tiny electric signal, you can give it the opposite direction. Okay, this is just, we are theoreticians, so we can play around with these ideas. So I have mentioned already you have these fractional excitation composites, which are appearing together for the same magnetic field, these MEE excitations, and then also we have this proposition for the measurements. And I think I will almost finish here. So there are some open routes and things we are doing. So we are looking at the quantum effects in ferroelectrics and also in multiferroids. So essentially what I said for the 2D case is that we dealt with Ising spins, okay? And there is now a big fuss about what quantum effects could do. For example, in these quantum, in these paraelectric materials that are almost ferroelectric. So quantum effects may play a role, and then one of the ideas is to include, for example, instead of Ising taking a transfer field, Ising to include quantum effects. Then most important to me is to get a better model, better description of a model which could change the magnetization with the electric field, which is what is important for technological applications. Then the other question is, okay, these were classical distortions. What happens if these guys become a quantum, real phonons, let's say? And this is another nice issue that appeared more recently, which is the lithium osmate, which shows polarization still being metallic. This is what is called polar metals. This was predicted by Anderson, as everything else, I think, a long time ago. And apparently in this material, it's been measured, okay? So they can measure an electric polarization while still keeping some conductivity, okay? So this is a very intriguing thing, and okay, one has to add electrons to this to see what happens. Then the 3D extension to go to nickelates, and this is what interested me more, which is field theory formulation. And just to make some advertising on some things, ongoing collaborations on Geneva and Willigen and Orsay-Jussier and Tbilisi are funded by a recent CNRS IRP project that we were granted. And there are 3 laboratories in France and 3 in Argentina that are taking part of that. And that's all. Thank you very much for your attention.
Questions? Questions?
Thanks for the talk. Many of these multiferroic materials are really sensitive to strain, so strain or pressure. Have you thought about whether the model will capture that? Because sometimes you can even separate the ferroelectricity and the magnetism.
You mean if we can consider external strain?
Yeah.
Yeah, that's a nice idea, but we haven't done
Not
this yet.
Okay.
But it's on the list, let's say. Yeah.
And for these nickelates, of course, they know the magnetic ordering already. They know they are antiferromagnetic and so on. But how about
Electric polarization.
The distortions?
Yeah.
Can they get that through neutrons, for instance?
Yeah, I think now they have some crystals. So before everything was in powders, but now they have some very small but crystals that can be measured, and they have seen, I think, both the formations that are of this type of dimerization in different directions, but they are also measuring now electric polarization, which is more difficult. So that's why you need single crystals, and it looks like there is a connection between these two variables. So I forgot, I had another joke that I forgot that I was going to say at the beginning of my talk. Let's go back to real condensed matter for your talk.
Okay, thank you. This was not the focus of your talk, but you mentioned these polar metals. I was very curious about this. How is it possible? Is it bad metal, few carriers? How does it work?
I think this is the main question, yeah, how that can happen. And I think this paper, I have to admit that this, for me, is very obscure. For me, not the paper. The paper maybe is clear, but I couldn't grasp something to explain with the fingers. Yeah. So my interpretation, but I'm going here now to something that I'm not sure, is that maybe some electrons contribute to conductivity, and these are not coupled to the lattice and the rest of the things, and those which are coupled and fixed somewhere here and there are those that produce this polarization. But still, I mean, there is always a question: how come that you have free electrons and don't screen the polarization? Yeah, but I mean, there are a couple of experimental papers where they see conductivity while they see polarization. So
Thank
that's
you.
all. You're welcome.
So I have a question. You very briefly mentioned in the 1D case that some bosonization results, and then I wonder if these very precise change of magnetization and polarization, that one goes down exactly when the other one spikes up, has to do with competing sign-Gordon potentials in your bosonized theory of the spin pairs Hamiltonian and the electric part of the Hamiltonian.
Okay, bosonization here is, let's see. So essentially, you can bosonize the magnetic part.
Yeah.
So the electric part is classical. So what you have, but let me tell you what happens just without the electric variables, okay? So without the electric variables, you have these deformations that will be modeled by some continuous field, okay? And density here is just the bosonized expression of this guy, okay? So this guy, so you know very well what it is. And then what you see is that here you have to get something commensurate. And playing with commensurability with the magnetization, then you can predict, so essentially you see, you get delta of X times this, in principle, if it survives, it will be relevant. So that means that the leading instabilities will have this shape. And then, well, you look, this is a bit technical, I can explain to you how it works. This was previous work. And then you can predict that you have this magnetization plateau and jump together. And then you see what happens. This is magnetization dominated scenario. And then you say, well, this is the magnetization picture. What happens with the polarization, with the dipolar variables? And then you see this. You could do the other way around. So first say, okay, these guys will fix first in some structure, and then see what happens to the magnetic variables. But this is this I didn't explain today. So essentially, what's going on here is that the magnetization part has this spin pairs-like structure. And since In this model, these dipolar variables are kind of spectators, okay? So they contribute to the energy, but they are driven by the magnetic system, okay? So the dynamics is in the magnetic part of the...
Right. I understand.
I understand your question because now we are trying to work with a model that has also these guys have dynamics, okay? So this will be kind of two-leg ladder,
Yeah.
coupled indirectly via lattice.
Via the
So
delta
this is
variable,
your
yeah.
question was
Yes.
pointing to that. But in this case, these guys are classic.
Okay, thank you.
Thank you.
Are there more questions? So if not, let's thank the speaker again.
Thank you.
So I think that's the last talk of the conference. So the organizers, do they want to say a word?